So at this point, we are basically experts at naming compounds. Okay, so we've gone through alkanes, we've gone through alkenes and alkynes and aromatic compounds, and we've taken a look how that all plays out in terms of refining and combustion. But I hate to tell you, there is still more functional groups that we need to know how to name these things in an organic compound. So the journey continues. Functional groups. Our first functional group that we're going to look at are called halides. We call them organic halides, obviously, because they're part of an organic compound. Now, we have, obviously, our halogens in these organic halides, which are fluoro, chloro, bromo, and iodo. So if we have chlorines, we use the suffix chloro. If we have bromines, we use bromo, fluorines, fluoro, and iodines, iodo. So that will be our guiding step as we go through how to name these, and we look at a few examples. So this is our first functional group, like I said, the halides. So organic halides, they can either be polar or non-polar molecules depending on how many halogens are attached to our parent chain. Okay, they have higher boiling points than similar hydrocarbons. They have very low solubility in water, but they have higher solubility than some similar hydrocarbons. So especially for smaller molecules, the smaller the molecule, probably the better solubility in water. Okay, and they're typically good solvents for organic materials such as fats, oils, waxes, gums, resins, and or rubber. So they're good solvents. They have generally low solubility, higher boiling points, and they can either be polar or non-polar molecules. So some examples. Now what we see is the general principle of how we name these compounds is the same. We like to name them in alphabetical order. We like to identify the location of our branches, and essentially we're just treating these halides as a branch off of our parent chain. So if we look at some examples, I'm going to draw out some examples that we have here. And I'm going to give you the structural formula, and then I'm going to give you the line formula. I figure, and maybe I'll give you a few examples where we do the condensed structural formula, but I'm going to skip a few of them just in the essence of saving some time. So our first example says 2,2,5-tribromo 5-methyl hexane. So the principle remains the same. We find our parent chain, which is this hexane. We know that we have one methyl group, and it's coming off the 5-carbon. And we know that we also have 3 bromo groups coming off of the 2, 2, and the 5 group of our hexane molecule. So I'm going to start by drawing out hexane. Okay, so I might just try and squish it in here. So I'm going to zoom in so I have lots of room. So hex meaning 6. 1, 2, 3, 4, 5, and 6. Okay, and I'm going to draw my 5-methyl branch first. Okay, and again, because I'm drawing it, I can choose which way I number it, and I'm just going to number it from left to right just to keep it simple. So this is carbon 1, 1, 2, 3, 4, 5, and 6. So off my 5-carbon, I have my methyl group. Now I'm going to try and keep the colors consistent so we know what we're doing here. And I'm just choosing to go down on this one here instead of going up. Okay, so we have the methyl group coming off our 5, and then we have 2,2,5-tri, meaning 3 bromos. So I have one on this carbon and I have another on this carbon. So there's 2 on each, coming off of both sides, up and down on our second carbon. So this is identified by a Br and a Br. So 2, 2, 5, so I need another one on my 5. 2, 2, 5, tribromo. So I have 1, 2, 3, tribromo, bromines on my 2 on my second, 1 on my 5th, and my 5 methyl group also coming off my 5th, my 5th carbon in my chain. Then, because we have an saturated, because it's an ANE, we have a saturated hydrocarbon, so I'm going to fill this up with hydrogens. Like so. So there is my structural formula for this, if I look at my condensed structural formula, we are going to do that in this sort of bluey green color, and it's the same as we've done everything that we've seen so far. So we can see CH3, C, okay, and either we can say CBr2 or we can just go like this, Br. I prefer to draw these out. Makes it a little bit better. Okay, then I have my CH2, my CH2, my carbon, my bromine, my CH3, and my CH3. Again, there's my parent chain as my hexane, and then my branches coming off of that. Now, if I'm to draw my line structural diagram of this guy here, I have hexane, so 1, 2, 3, 4, 5, and 6. Again, I have no double bonds. I don't need to worry about that. Off of my 5th carbon, so 1, 2, 3, 4, 5, I have a methyl branch. Now, the way that I draw out my bromo branches are essentially the same way that I would draw out a methyl branch, except I have to indicate that there is a bromine coming off of it. So it's off of my 2nd, so I have a bromine coming off of my 2nd, and once I write down that there's a Br attached to that, I know that it's not an alkyl group. It's not a carbon-based group. So that tells me that, and then I also have one coming down out of it. Okay, and then I also have another one coming out of my 5th carbon like so. So as long as I indicate that there's something at the end of that branch that is not just a point, it's because if it was just a point, it would be carbon, then it's good when I go to name this. Okay, there's our first example. Let's take a look at our second example. Oops, here we go. So same concept. We have, oopsies, ethane. Okay, again, it's saturated. It's no double bonds or anything in there. And we have a lot of stuff to look at here. We have 1,1,2,2 tetrafluoroethane. So we have F. And we also have 4. So we have 4 fluoros. And they're at the 1,1,2,2 locations. I also have 2 chloros, okay, again, 2 chloros at the 1 and 2 location. So as always, I'm going to start by drawing out my parent chain, and again, I'm going to zoom in so I have lots of space here. So F is 2, so I have 2 carbons, 1 and 2. So 2 carbons here, and I have, let's start just with our dichloro. So I have 1, 2, dichloro, and I'm going to use orange to be consistent. So this is carbon 1, this is carbon number 2, I have chloro, and then I have 1,1,2,2 tetrafluoro. So I'm going to do that in pink, 1,1,2,2 tetrafluoroethane. Now notice this is still considered ethane, it's still saturated even though there's no hydrogens in it. Okay, again, you get the idea on the condensed structural formula, and if I was to draw a line diagram for this, it would be pretty messy, but essentially I would have F, F, C, L, C, L, F, F. So I have 1,2,1,1,2,2 tetrafluoroethane. Bet you never thought you would have known how to draw on that. So that's pretty cool and exciting. Let's take a look at this last example here. Same principle. Okay, our parent chain this time is our benzene ring. This will be a good one to take a look at. So we have our benzene ring, and we have 1,2-dichloro. So we have 1, 2, we have 2 of them, and it's our chloro group. So similar principles here. I'm going to zoom this guy in as best as I can. So if we draw our benzene ring first, and I'm just going to draw it in the simplified version, like so. So there's our benzene ring. If I just consider this first sort of top carbon here to be carbon number 1, and then carbon number 2, I can just list off my dichloros in that way. So I have 1, 2, dichloro. 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 1, chlorobenzene. So that one's pretty simple. Now, the line diagram is going to be identical to my structural diagram that's here. And if I was to draw out the full structural diagram, I would draw a hydrogen coming off of each of these, and I would show the double bonds in that compound. So that is our few examples that we've gone through now with naming halides. Okay, let's just take a look at the reverse. Let's look at the diagrams and see if we can try and name them. So our first example, I'm going to number from my right to my left this time because it looks just based on the diagram. If I was to count from left to right, it would be 1, 2, 3, and 4 for this first guy. Whereas if I count from the right, I have 1, 2, 3, and 4. So the lowest numbers will be for if I number from my right to my left. So this is covered 1, 2, 3, 4, 5, 6, and 7. So that tells me my parent chain is heptane. I don't see any double bonds, so it's an alkane, it's an ANE. And I see that I have I need to list in alphabetical order to be consistent, so I have my 2 bromo and my 4 chloro, and I will list them from B to C. So I have my bromo, and we'll do pink chloro. So I have 2 bromo, and then I have 3 chloro heptane. All right. So that one was pretty easy. You can see that sometimes it's easier to draw them and sometimes it's easier to identify them, and you have to be familiar with both. So it's a good thing we're going over some examples. Okay, this guy here, we see that we have our parent chain probably being this guy here. The reason being we have a double bond in that parent chain. We also have a branch coming off that parent chain here as well as here. So the way that we name this is we have 1, 2, 3 carbons in our parent chain. And if we number these carbons, I'm just going to actually erase this line here. If we number our carbons with giving our bond priority, we number them 1, 2, and 3. So when we go to name this, we have our parent chain as propane. Okay, but because we have a double bond, it's actually propene. Okay, I could put prop-1-ene, but because in this case it will be a little bit redundant, I'm just going to keep it simple with propene. If you put prop-1-ene, that's also good, no problem. Okay, so propene, and then I see that I have a chloro branch, and I also have a methyl branch. So I have my chloro branch and my methyl branch. Now, again, because I want to label these in alphabetical order, I'm going to say 3 chloro, because it's coming off of technically this third carbon right here. So I have 3 chloro, and then I have 2 methyl propene. Again, that's all sort of one word. There's a bit of a space there, but that's okay. So 3 chloro, 2 methyl propene. So that is our functional group on halides. Let's continue on. We can take a look at our next functional group of alcohols. Now, all alcohols contain only one functional group. We're not dealing with a bunch of different ones like with our halides. And that functional group is called a hydroxyl group. And that hydroxyl group is an OH coming off of our carbon chain. Now, please don't get confused that this is not OH negative. It's not hydroxide. It's hydroxyl. Okay, so it's not an ionic compound. We're dealing with it as part of a carbon chain as an OH group. Now, be careful, it does have to be OH kind of on its own to be classified as a hydroxyl group or an alcohol. And in general, we end our alcohols with an OLS or an OL at the end. So they're alls, so methanol, ethanol, propanol, things like that. So let's take a look at some examples. Similar to our naming of our bonds, we put our all at the end. We name our all at the end or the suffix of our compound. So if we were to look at butanol, butan-1-ol, I'm going to zoom in here again. I start with my parent chain being butane. okay, butane, and I have the alcohol coming off of my first carbon. In this case, I'm going to choose this carbon as my first carbon, and then the rest are hydrogens. Again, if I was to draw out my line diagram, I would see 1, 2, 3, and 4. And off my first carbon, I would see an OH group. Okay, again, as long as there's something indicated after this line here, it means that it isn't a carbon, that it is just this hydroxyl group. Okay, let's look at methyl propan 2-ol. So again, propan is our parent chain. So we have propane, 1, 2, 3, and we have the alcohol coming off of the second carbon, so we can draw OH. And we have a methyl group. Now, a reminder, we can't add a methyl group onto either of our terminal carbons. It has to come off of our middle carbon. Otherwise, it would be, I should draw this differently. Otherwise, it would be a 4-carbon chain instead of a 3-carbon chain. So I see that I have methyl propan 2-ol. And if I was to draw a line diagram for this, again, I have prop 1, 2, 3. Sort of looks like a top of an arrow. And I have my OH group coming off my center, as well as a methyl group coming off my center. That's how I would go about drawing those two. If I look at some other examples here of naming these, same thing goes. Always find my longest parent chain. Which is this guy here. I would say, so in this group, in this alcohol, I would say it's butan 2-ol as my sort of parent chain. I have 4 carbons in that parent chain, so it's butan, and it's 2 because it's coming off my second carbon. If I name them from 1, 2, 3, okay, I give priority to that alcohol. So butan 2-ol. And it's a methyl group coming off my third carbon, so it's 3-methyl butan 2-ol. Take a look at this guy here. I see that my longest parent chain is here. Okay, so when I see that, it looks like I have again butanol, butan 2-ol. Again, if I name from right to left, and I'm going to also have 2,3 dimethyl butan 2-ol. Okay, so there's our few examples on both how to draw them and how to name them so far. Now we can actually classify our alcohols into 3 main groups. We can classify them as primary, secondary, or tertiary alcohols. Now this is dependent on the number of carbon atoms that the carbon that the hydroxyl group is bonded to. Now I know that sounds really convoluted, but it's not that complex in reality. So we have to look at what carbon our hydroxyl group is bonded to, and then we count the other carbon atoms that are surrounding that carbon. So with our first example here, we see that this carbon, okay, is only attached to one other carbon here, okay? So this carbon is attached to our first carbon here. So since this hydroxyl group is attached to a carbon that only has one other carbon attached to it, we call this a primary alcohol, okay, primary. Now, if we look at a secondary, it'll make a little bit more sense. We see again our main carbon in the middle here, and we see that there is 2 carbons that are adjacent or touching the carbon that our hydroxyl group is attached to. So we see our hydroxyl group in both examples. We go to the carbon that it's touching, okay, or that it's attached to, and this one has 2 carbons where this one only has the 1. That makes this a secondary alcohol. Okay, you get the idea. As we go on to our tertiary alcohol, we see this carbon is attached to 3, or this hydroxyl, I guess I should say, this hydroxyl is attached to a carbon that has 3 additional carbons bonded to it. So we have 1, 2, 3 bonded to this carbon where the hydroxyl group is bonded to. Okay, again, we see our hydroxyl making this a tertiary alcohol. Okay, so there's our 3 types of alcohols, and in general, you won't have to, it has nothing to do with naming, it is just identifying the differences between these 3. So primary, tertiary, and secondary alcohols. Okay, we're not quite through with alcohols. There's something else that we need to take a look at, and it is called polyalcohols. Now this is when we have more than one hydroxyl group, okay, involved in our alcohol. Now what you'll notice is the naming is a little bit different. We are actually able to include our E, and this is just based on the English language. When we had the ethanol, okay, we knocked off the E usually because it would be ethanol, and based on English, we don't want that many vowels together. But when we have a polyalcohol, where we put a prefix on how many alcohols we have, we're able to jump that E back in there. So we call it ethane. So if I look at my example here, I'm just going to erase what I just drew on there. Same thing goes. We start with our parent chain. We see that our parent chain has 2 carbons. Okay, which means that it's ethane. So in this case, I can write ethane, and I have 2 hydroxyl groups coming off of, and that's coming off of my first and second carbon. So I have 1, 2 diol. I have to identify that there's 2. So I always start with my parent chain. Now, because the alcohol is a suffix, I can say ethane 1, 2 diol in this example. Okay, so I can identify my alcohol like that. Let's take a look at another example. This one's even crazier. Again, my parent chain here is this propane, so I can write propane. It looks like I have hydroxyl groups coming off of carbons 1, 2, and 3, and I have to identify with a prefix how many alcohols there are, so it's propane 1, 2, 3 triol. All right, we also call that glycerol. Okay. Let's take a look at a few more examples, I think. So we have butane 1,3-diol, which would look something like this. Okay, butane, 4 carbons. Actually, let me erase that. We'll do this so we have lots of room for a few different drawings here. Butane. Oops. 1, 2, 3, 4, and we have 1,3-diol. So 1,3 tells us the location. Di tells us how many. Tells us it's an alcohol. So I have a hydroxyl group coming off of 1 and 3. Hydroxyl. Hydroxyl, and the rest should be filled in with hydrogens. So this is butane, because we have 4 carbons, 1,3-diol. Take a look at propane 2,2-diol. Oopsies, here we go. So I have propane, and I have 2,2-diol, telling me that I have a hydroxyl group coming off of the top and the bottom of this center carbon, my second carbon. So then the rest is filled in with hydrogens. All right. So it is a little bit weird that we have this E added on here compared to our alcohols in our first examples, or without, they were just mono alcohols or 1 hydroxyl group, but that's okay. We can add our E in, we can say how many there are, and the location with the diol or triol or tetraol or whatever it might be at the end. Okay, generally you won't see examples of more than triol in this course, but you should be aware. Okay, if we're going to name this guy here, same thing goes. We have 1, 2, 3, 4, and 5 carbons there, and it's in a circle. Okay, so we know that this is cyclopentane. And we see that we have a hydroxyl group here and a hydroxyl group here, and we'll call that carbon 1 and 2. So we have cyclopentane 1,2-diol. All right, when we go to name that. So we can look at a variety of different alcohols as polyalcohols or just regular alcohols and the different ways of naming them. Let's continue on. A new group, we have a carboxylic acid. Now, carboxylic acids have a COOH group. Okay, now the COOH group, or our carboxylic acid group, is formed from a carbonyl group, which is a C bonded to an O. It's a double bond to an O, pardon me. And then we have our hydroxyl group, which is bonded off of that carbon as well. So we have a carbonyl group and a hydroxyl group, and we create a single word from that, getting us as a carboxyl group. So we call a carboxyl group as a carboxylic acid, okay? And we call these blank oic acids. So we generally end with an oic acid at the end as a suffix of our naming system. So again, we definitely want to see the COOH. Notice again that we have this double bond here between our carbon and our oxygen atom. So if we look at ethanoic acid, we would say that we have two carbons. Okay, we have a carbon bonded to a carbon. And off of one of our carbons, we don't add an additional carbon. Okay, we just base it off of what we have given here. We have our double bonded O and our single bonded OH, okay, which makes this ethanoic acid. Now here I need to continue to fill this out here. So we see that we have ethanoic acid. Butanoic acid, similarly, but meaning 4. 1, 2, 3, 4 carbons, double bonded oxygen, single bonded hydroxyl group. Fill the rest in with hydrogens. Okay, so we have ethanoic acid and butanoic acid. We can continue our naming here as we go through. Please notice that again, we don't need to add a COOH group. We simply just add the O double bonded to our terminal carbon and the OH bonded to a terminal carbon. So taking a look at this example over on the right, we see propanoic acid, okay, because we have 1, 2, 3 carbons, and we have our O and our OH group as a terminal carbon. And then if we take a look at our bottom example, we have 1, 2, 3, 4, 5, 6 carbons, so it's hexanoic acid. Okay, hexanoic acid. Now, naming esters. Okay, when we name esters, essentially an ester is formed from the reaction of a carboxylic acid and an alcohol. So that is where we get our esters from. So esters are kind of an odd thing. It has an interesting naming system, and often students find these to be more on the challenging side. So if we look, we will look more at this style of reaction that I have listed down here, which is an esterification reaction, which we'll go into when we talk about organic reactions. I just want to get an idea of how to name these things here. So if we go to name methyl butanoate, so the trick here is when we're naming these things, we need to identify which is the branch and which is our parent chain. So I always like to look at my butanoate as my parent chain, or my ethanoate as my parent chain, or my heptanoate as my parent chain. Okay, the methyl group is going to be a branch that's coming off of our parent chain. Okay, so I'm going to sort of draw these out, and I'm going to go through what they look like. So my butanoate, now if I jump back to what my ester group looks like, it has a COO group. And notice when we look at our ester example here, we see that we have our carbon bonded to our oxygen, double bonded to our oxygen, and it's single bonded to an oxygen here. Now notice that there's a chain of carbons on either side of this group. Now that is very important. You'll see some level of carbons on your left side of your ester as well as on your right side of your ester as we go through. And like I said, these things are called OAtes. Okay, so again, the difference between this and our carboxyl group is the H that's at the end of this, and instead of there being an H back here, there's a branch of carbons. So when we go to name these, always start with your parent chain. So we start with butanoate. So in this case, I'll draw bute, 4 carbons. Okay, my O8 portion, I'll do in pink. All right, so my O8 is again this double bonded O and a single bonded O. That's my O8. The methyl group, which I'll identify in green, okay, is the branch that comes off of our oxygen that requires more bonds. Now what you'll notice is that this oxygen is happy with 2 bonds. It has only a bonding capacity of 2. This carbon is happy with 4 bonds, but this oxygen requires another bond. So what we do is we add on a methyl group, okay, which is CH3, onto that oxygen to make that oxygen happy. So this methyl group is a branch of our parent butanoate. So then I go back, I fill in the rest with hydrogens, okay, making this methyl butanoate. Starting parent chain, butanoate, my O8 is this 2 O's, 1 double bonded, 1 single bonded, and then I add my branch off of that. Okay, well let's get a little bit more complex. Okay, I have ethanoate, eth meaning 2, so I have 1, 2. Again, I'm going to identify my O8 with my pink. So I have my O8, and I'm going to know that this is full of hydrogens as well. But then it says 3-methyl-butyl ethanoate. So what does that mean? What that means is I have a 3-methyl branch coming off of this butyl branch. So I know that I have bute, meaning 4. 1, 2, 3, 4. And that off of that 4 carbon branch, I have a branch off my branch. So off of my 3rd carbon, 1, 2, 3, being consistent naming from this direction, my left to my right, I have a 3-methyl-butyl, which looks like this, ethanoate. Okay, so there's lots to look at there. Okay, if I take a look at this, I have ethyl heptanoate. Again, heptane being 7, O8 I'll put in pink, and my ethyl I'll put in green. Heptanoate, 1, 2, 3, 4, 5, 6, and 7. My O8, double bonded O, single bonded O, and I have an ethyl, 2 carbons. Eth meaning 2. The rest of these guys I fill up with hydrogens like so. So ethyl heptanoate. Now when I go to draw these as a line diagram, they become again a little bit weird, but we'll show you how to do that. So methyl butanoate, again I'm going to start with that parent chain, 1, 2, 3, 4 for bute. Off of that 4th carbon, 1, 2, 3, 4 here, I have my double bonded O. Again, as long as I indicate it's something other than carbon, it's okay. Okay, and then I have my single bonded O with a carbon there. So again, because at this point I didn't indicate that it was anything other than a carbon, it simply is a carbon branch. So then that is a methyl branch. That's how that guy would look. 3-methyl-butyl ethanoate. Again, 1, 2 with my double bonded O, my single bonded O, and then I have from this 1, 2, 3, 4, so 1, 2, 3, 4, and off of my 3rd carbon I have a branch. Okay, so that is how I would draw this guy. So this doesn't represent a carbon, this is still attached to this oxygen, this atom here. So then there's 1, 2, 3, 4, and then there's this branch here that is methyl butyl. Take a look at our last example. I have 7 in my parent chain. 1, 2, 3, 4, 5, 6, 7. Double bonded to an O. Single bonded to an O with a 1, 2. Okay, again, 1, 2, 3, 4, 5, 6, 7 in my parent chain plus 2 on that branch coming off of it. All right, let's go to name this guy on the side. We see that our parent chain is actually a benzene ring. So we would call this benzoate. Okay, so we have benzoate. Now we see that there's 1, 2, 3 carbons coming off of that. So we call this propyl benzoate. All right, so again, that is a little bit more complex how we name and draw these. Definitely recommend going to practice some questions out of the textbook for any of our functional groups that we've taken a look at. Again, our esters are related to our carboxyl groups as well as our hydroxyl groups because it is a combination of those two sort of carbons, hydrocarbons. So we'll definitely take a look at organic reactions as we continue through this unit, but you should be quite familiar with how to draw each of these functional groups as part of a hydrocarbon chain. So if you need to go back and rewind, do so now, take some notes, and do some practice questions. Good luck.